Lecture 45, Folds. Folds are bends or flexures of layered rock. They form in response to motion along faults, diapirism, compaction, and regional subsidence and uplift. Folds are important. As an example, 80% of hydrocarbons are in folds. Curvature is a great concept to understand folds. To begin, we consider the curvature of a line at point P1. If we trace normals to the line at point P1 and some nearby point, P2, the normals will intersect at a distance, r1, from P1. We define the radius of curvature, r, at point P1, as the limit to which r1 approaches, as we make P2 closer and closer to P1. The curvature of the line is the reciprocal of the radius of curvature. Thus a straight line has an infinite radius of curvature and zero curvature. Conversely, a very tight fold has a short radius of curvature and large curvature. We can define positive and negative curvatures by defining the radius of curvature on one side of the line to be positive and on the other side to be negative. There must be an inflection point of zero curvature between 2 points of opposite curvature sign. We can now consider three-dimensional curvature at any point, P1, on a curved surface. Of all the lines passing through that point, one has maximum curvature, C max, and one has minimum curvature, C min. These are called the principal curvatures of the surface at point P1. The Gaussian curvature is the product of the principal curvatures. We can define three classes of points on a surface based on the Gaussian curvature. An elliptic point, P1, has positive Gaussian curvature. A hyperbolic point, P2, has negative Gaussian curvature. And a parabolic point, or cylindrical point, P3, has zero Gaussian curvature. Most natural folds in rock are cylindrical or parabolic throughout. They have a minimum curvature very much smaller than the maximum curvature. Gaussian curvature has the interesting property that for any deformation in which the surface is not stretched or compressed, the Gaussian curvature remains unchanged. A flat layer has zero Gaussian curvature. The only type of point for which the Gaussian curvature is still zero after folding is a cylindrical point. Points on folds that are elliptic or hyperbolic must have undergone stretching and compression of the surface. Knowing the concept of curvature, we can define key elements of the fold. The fold axis is the direction of line of minimum curvature. In cylindrical folds, the fold axis is a line of zero curvature. The hinge is a point of local maximum in curvature along a line of principal curvature. The hinge line is a line of principal curvature, passing through a set of local hinges. The axial surface is the plane containing the hinge lines. The inflection point is a point of zero curvature along a line of principal curvature. And the inflection line bounds areas of positive and negative curvature on each folded surface. Cylindrical folds are those in which the surface can be generated by moving a line parallel to itself through space. This line is parallel to the hinge line and is called the fold axis. In fact, only cylindrical folds have a fold axis. On a stereonet showing the bedding planes, or beta diagram, the bedding planes intersect at the fold axis. On a stereonet showing the poles to bedding, or pi diagram, the poles fall along a great circle. This is the profile plane of the fold, and the pole to the profile plane is the fold axis. In a cylindrical fold, the line of zero curvature is the fold axis. Because the fold axis is uncurved, all sections perpendicular to it must be identical. If we know the orientation of the fold axis, we can construct a true profile view of the fold from any arbitrary cut through the layers. This is the down plunge projection of the fold. We solved this problem before using linear algebra. To construct the down plunge projection of the fold, we just need to transform points on the fold, from east, north, up coordinates, to a coordinate system with x'3 along the fold axis, and x'1, x'2 defining the profile plane of the fold. In the lab, we will construct the down plunge projection of this anticline. Another type of folds are conical folds. The folded surfaces in these folds are in the shape of a cone. The folded layers converge to a point, beyond which the fold does not exist at all. Thus, the shortening due to folding of the layers changes along the hinge line. Conical folds are commonly found at the tip line of faults. In a beta diagram, the bedding planes do not intersect at the fold axis. In fact, the fold axis is not on the fold, but it is a geometrical construct. In a pie diagram, poles to bedding fall along a small circle, whose center is the fold axis. The angle between the fold axis and any of the poles is the same. The orientation of a fold can be described by the dip of the axial surface and the plunge of the hinge line. An upright fold has a vertical axial surface and horizontal hinge line. A vertical fold has a vertical axial surface and a vertical hinge line. A recumbent fold has a horizontal axial surface and a horizontal hinge line. Between these three end members, there are other types. The intersection of the axial surface of the fold with a plane is the axial surface trace of the fold on that plane. This figure shows the axial surface trace of a fold on a horizontal plane and on a vertical plane. The intersection of the axial surface of the fold with the surface topography is called the surface axial trace of the fold. Folds can be also described by the angle between their limbs, or interlimb angle. Isoclinal folds have interlimb angle between 0 and 30 degrees. Tight folds have interlimb angle between 30 and 70 degrees. Open folds have interlimb angle between 70 and 120 degrees. And gentle folds have interlimb angle between 120 and 180 degrees. The pie diagram with bedding poles on a stereo net is a great way to visualize the geometry of a fold. Figure A shows a dipping plane with bedding normals. The poles in this case plot on a small area in the stereo net, reflecting small variations in the orientation of the plane. Figure B shows a near cylindrical fold with normals. The poles in this case define a great circle, with variations reflecting the departure of the fold from a cylindrical structure. On an equal area stereo net, bedding poles can be contoured as indicated here. In the old days, this was done manually using a grid and a counter. These days, it is mostly done using a computer program. These figures show the pie diagram for an unfolded, slightly inclined bed, a gently plunging and gentle fold, and a gently plunging and open fold. Notice how the contours to bedding poles change with decreasing fold interlimb angle. These diagrams show the variation in pie diagrams, with change in fold form. A is a fold with broad, rounded hinge. B is a fold with narrow hinge. C is a chevron fold with two planar limbs and angular hinge. And D is an asymmetric fold. In D, the gentler and longer fold limb is indicated by the higher contour values, since there are more bedding measurements on this plane. The upper diagram shows how to determine the orientation of the fold axial surface from a pie diagram. The bedding poles define a great circle. The axial trace contains the pole to this great circle, the fold axis, and the axial trace. On a contoured pie diagram, the axial surface contains the fold axis, and bisects the bedding pole concentrations. The lower diagram shows the variations in position of the bedding pole girdle, with changes in the orientation of the fold axis and the axial surface. A is a non-plunging, upright fold. B is a plunging fold. Note that in these two cases, the axial surface is almost vertical. C is a plunging inclined fold, and D is a plunging overturned fold. In D, notice the presence of vertical beds indicated by poles on the primitive. E is a reclined fold, and F is a recumbent fold. In this last case, the axial surface coincides with the primitive. In asymmetric and overturned folds, the concept of vergence is important. The vergence of a fold is the direction that the shorter, more steeply dipping limb of the fold faces. For the structure shown here, the vergence of the smaller Z and S folds is indicated by the blue arrows. The stratigraphy is fundamental to define a fold. Without knowing the stratigraphy, we can just describe the form of the fold, using terms such as those for figures A to C, monocline, synform, and antiform. If we know the stratigraphy and the fold faces upwards, we have two types of folds, figure D, or syncline, where the youngest rock unit is at the core of the fold, and figure E, or anticline, where the oldest rock unit is at the core. If we know the stratigraphy and the fold faces downwards, we have two types of folds, figure F, or synformal anticline, where the oldest rock unit is at the core of the fold, and figure G, or antiformal syncline, where the youngest rock unit is at the core of the fold. These terms are summarized in figure H, which shows synforms and antiforms for a fold facing both upwards and downwards. In a plunging fold, the fold hinge is inclined from the horizontal. Erosion of plunging folds produces a nose or V in the ground. In a plunging syncline, the nose points in the direction opposite to the plunge of the fold axis, while in a plunging anticline, the nose points in the direction the fold axis is plunging. These are the symbols used for folds on geologic maps. A shows the symbols for major folds. B shows the symbols for plunging folds, and vertical to inclined axial surface. And C shows the symbols for minor folds, with the arrow showing the plunge direction of the fold. This is a geologic map of folds in the Appalachians of Virginia. Can you tell the different folds in the map? In which direction is the Rye Cove syncline plunging? These are folds on a seismic time slice. The closed structures on the time slice are folds, and they may be anticlines or synclines. To learn more about this topic, read Chapter 12 of Fossen, and do his e-learning module on folding. And answer these questions.